Hello everyone. Today we shall be covering Thermodynamics Lesson 7, where we cover heat pumps, refrigerators, and heat cycle examples. So we're going to cover how would you solve one of those types of heat cycle, basically. But we're going to cover the control volume aspect of it. So, because last time we covered how you would solve a control mass. And the control volume is usually what you're going to be covering because those are refrigerators that you see in your home, heat pumps when you have your refrigerator the opposite direction, and power plants, air turbines, that type of stuff. So we're going to cover control volumes systems. So as you can see here, I have a condenser removing heat from the system up top. I have a compressor right here where work is being pumped in onto the fluid, and I have an evaporator here where energy is being pumped into the system. So how do you tell, well, first off, what is a cycle? Is it a heat engine or is it a refrigerator heat pump cycle? Well, because there's a compressor, only one compressor, no turbine, just a compressor, pumping the fluid, putting it at a higher pressure, that is going to usually be a refrigeration cycle. Because there's just one thing. Simple parts. Now, as you can see, if the condenser, I'm pumping heat out of my fluid, and at the evaporator I'm pumping heat into my fluid. Well, that doesn't tell you whether it's a refrigerator or a heat pump. So you'd have to look at the wording. I don't have the wording here because we just want to learn how to analyze these cycles. But if I told you I was removing heat from a room, for example, like a refrigerator, well, to be removing heat from somewhere, you have to be adding it to something else. So, if I was looking here at my evaporator, I'm removing heat from my room and pumping it into my working fluid through the evaporator. That is then your refrigeration cycle. You would care about how much heat you're removing from your room and how much work does it take to do that. Now let's say I want to heat up a room. That is a heat pump. So I'm looking how much heat leaves the system, because to pump heat into something, it has to leave something. Well, that would be my condenser up here at the top. Here. I'm pumping heat into my environment over here, my environment. So if I want to know what my coefficient of performance for my heat pump, I would look at my Q out and the work required to remove that amount, or to pump in that amount of heat. So we're going to find Q in and Q out, we're going to draw a TS diagram, we're going to find the coefficient of performance if it was a refrigerator, we're going to find the coefficient of performance if it was a heat pump, and we want to know how to turn this into a heat engine and what would its efficiency be. So some preliminary information we are given. Here at state point 1 is before it goes into the compressor. We are dealing with refrigerant 134A. Our pressure here at state point 1 and our pressure here at state point 4, because as you go through an evaporator, you do not lose pressure. That is going to be 2.4 bar, and we're going to have a mass flow rate of 7 kilograms per minute going through this entire system. We have the work going into the compressor to pump that fluid up to a higher pressure is 5.17 kilowatts, and we will be pumping it up to 9 bar, and there is no loss of pressure across the condenser. There is loss of pressure across the valve. However, we're going to consider the valve to be isentropic. Well, what does isentropic mean? That means there is no entropy loss from state point 3, not entropy, sorry. There is no enthalpy loss, which is H, from state point 3 to state point 4. Therefore, H at 3 is equal to H at 4. And we're going to assume that our compressor is going to be isentropic, which, if you recall, isentropic means that there is no heat exchange between the fluid and the surrounding environment, and there is no entropy change. So you can think about it as the compressor is really insulated. So let's analyze the system. Well, before we analyze the system, we need to draw a TS diagram. So let's do that. Alright. T, S, let's draw my dome. And if you recall earlier, I said we're operating between 9 bar and 2.4 bar. Oh, that's not straight. Well, here, let's extend this dome line. So, when you are dealing with compressors, heat engines, that type of stuff, usually when you're leaving an evaporator for an ideal cycle, you're going to be at saturated liquid. Or not saturated. You're going to be at saturated vapor before you go into the compressor from the evaporator. So my state point 1 is going to be right here. And then recall, I said that the turbine is isentropic, which means that there is no change in entropy. So I draw my line straight up to there. This would be my state point 2 up here. Now I'm cooling it down from the condenser, and I'm going to cool it down to saturated liquid here. And then recall, H3 is equal to H4 because it's isentropic. But you may ask, well, John, I have a TS diagram. How would I draw an isentropic process? Well, this is how. You would draw a curve going down to your point here. And where 4 is depends what the enthalpy is of state point 3. Because it's at a higher pressure, usually 4 is going to be some mixture of saturated liquid and saturated vapor, so it's going to have some sort of quality attached to it. And if you needed to, you would find it. I'm going to tell you when do we need to find it and when do we don't. So this is our TS diagram for our process. Well, now we need to find Q in and Q out before we can do anything. Well, to do that, we need to know the values at each state point. So let's do that. We have state point 1. My pressure is 2.4 bar. My temperature, let's go to our tables. For 2.4 bar, it's going to be negative 5.37 degrees Celsius. My enthalpy is going to be 244.09 kilojoules per kilogram, and my entropy is going to be 0.922 kilojoules per kilogram. Okay, now state point 2. So my pressure is 9 bar. Oh, I should label that up here. So state point 2, my pressure is 9 bar. My temperature, I was told, was 60 degrees. My entropy, because it's an isentropic turbine, is the same as state point 1, so it's 0.922 kilojoules per kilogram. Well, what's H2? What's my enthalpy at that state? Well, I know my pressure, I know my temperature, so if I were to go to an engineering table, I would see that my entropy has to be 0.922. But if I look at the saturated liquid and saturated vapor table for refrigerant 134A, I get that my saturated liquid entropy is 0.9054. So if I'm above that, I must be in the superheated region, as shown here in this diagram is what I expected to find out. So I go to 9 bar, or actually I didn't even need this, because I made that assumption. This is where I was wrong. I made this assumption that it was an isentropic process. I didn't know. I also didn't really care because I was given a pressure and a temperature. Never assume a turbine is isentropic. That is the mistake I made here. Never assume that at all because you don't know if it is. But that is why they gave you a pressure and a temperature. I made that mistake. I rectified it, but I made that mistake. So if I go to my refrigerant 134A for 9 bar at 60 degrees, I get that my enthalpy here is equal to 293.21. And notice my entropy here, if you were to look at that table, is 0.9897 kilojoules per kilogram. Notice they're not the same at all. Therefore, there is a change in enthalpy of this compressor. It is greater than 0. Therefore, this is not an isentropic turbine. I made that mistake, and I apologize. So, now we need to go over state point 3. So, state point 3. Well, if you recall, still 9 bar. I'm at the saturated liquid line, as you can see here, and from that problem. Therefore, go to 9 bar at saturated liquid. You're at a temperature of 35.53 degrees Celsius, and my enthalpy at 3 is equal to, let's see, 99.56 kilojoules per kilogram. And now I need to know state point 4. Now, do I care about what the entropy is at state point 3? I mean, I cared about it when it was at state point 1 and state point 2. Well, I shouldn't have cared about it when it was at state point 1 and state point 2. But let's assume I wasn't given the temperature and that it was an isentropic turbine. Well, to solve that type of system, I would need 2 points. Remember, you needed 2 points that are independent of mass and independent of each other. So that would be what your entropy is. At state point 3, I know I'm at 9 bar and I know I'm at the saturated liquid point. So I don't need the entropy. And I'm not going to use it, as you will see. So I just need the enthalpy. You'll see why too in a second. And then state point 4, pressure equals 2.4 bar. I'm in the dome, somewhere along the line I have some sort of quality. So I go to 2.4 bar, my temperature is negative 5.37 degrees Celsius, and my entropy, remember because it's an isenthalpic valve, H4 is equal to H3, which is equal to 99.56 kilojoules per kilogram. Alright, now why do I not care about entropy? Well, if I wanted to find Q in and Q out, I have to use the first law of thermodynamics for a control volume, because I have a mass flowing here, so I can't analyze what's going on with the mass because I would be analyzing the entire system, and you can't do that. Well, you can do that, but it gets really, really complicated really fast. So I'm going to do control volume of each individual part. So I'm going to do control volume for the compressor, control volume for the evaporator, control volume for the condenser, and for the valve. You don't need to for the valve, but we're going to do it anyway. So let's do this. Let's show, well, why do we need the enthalpies? Well, if you recall, first law for control volume is equal to Q dot minus work dot plus M dot in, enthalpy in, plus kinetic energy in, plus potential energy in, minus M dot out, enthalpy out, plus kinetic energy out, plus potential energy out. Well, I said you can neglect kinetic and potential energy, so 0. And this is at steady state, so 0. So my equation is 0 is equal to Q dot minus work dot. Now, there's one pipe going into each system, one pipe in, one pipe out, and I know my mass flow rate is 7 kilograms per minute. Therefore, m dot in and m dot out must be the same. So I simply get plus m dot times enthalpy in minus enthalpy out. And this here is the first law that you will be using when you're analyzing these types of cycles. You can derive it every single time you want because you're going to be neglecting kinetic and potential energy, and you'd always arrive at this equation down here. Now you might ask, well, John, what happens if I can't neglect kinetic and potential energy? Well, your problem gets much more complicated, and I recommend you checking out my video on the derivation for Bernoulli's equation, because in that video I do not neglect kinetic and potential energy, and I show you how to handle it. I will link the video in the description here for you to see. So let's continue on with this problem. So I need to find Q in and Q out. So do I care about the compressor? I do, for the work that you have to pump into the system, because I only care about Q out of the condenser and Q in of the evaporator, because that's how much heat I'm pumping into my system or I'm removing from my system or my environment. That type of stuff. So for the compressor, I just care about how much work is being used. Well, the problem gave me that a work of 5.17 kilowatts is being used. So I'd come over here, compressor, work is equal to negative 5.17 or 75? 5.17 kilowatts. Now I don't need to do first law because I do not care about the heat. I don't. It doesn't matter. It doesn't affect my system how much heat is lost through the turbine, because I just care about how much heat is leaving through the condenser and being absorbed in through the evaporator. So let's do that. Let's analyze the condenser. So I have my condenser here. I have some heat leaving the system. I have state point 2 leading into the system. I have state point 3 leaving the system. Let's analyze it using the first law of thermodynamics. So 0 is equal to Q dot minus the work plus m dot times inlet H2 minus outlet H3. Now, in a condenser, there are no moving parts. So if there's no moving parts, the fluid can't do any work. So the work here is 0. So there's clearly some heat leaving through the condenser because I'm condensing the fluid, and I have an enthalpy change. So I have Q dot is equal to m dot times H3 minus H2. Oh, that's wrong. Sorry. Q dot is equal to negative m dot times H2 minus H3 here, because I'm just subtracting that over. Distribute the negative. Q dot is equal to m dot times H3 minus H2. Plug in my variables. I have 7 kilograms per minute times H3, which is 99.56 kilojoules per kilogram, minus H2, which is 293.21 kilojoules per kilogram. Alright, so my Q dot is equal to, let's see, there we go, 99.56 minus 293.21 times 7, I get here negative 1355.55 kilojoules, kilojoules per minute. So that is how much energy is, or how much heat is leaving my system through my condenser. This is Q out. So that is one of the things I had to find was Q out. Now I need to find Q in. Well, where's Q in? If you look up here, Q in is at the evaporator. Well, that's state point 4 to state point 1. So come down here, analyze the evaporator. I have my control volume I have to draw. I have 0.1, 0.2. So Q0 is equal to Q dot minus the work plus M dot times H2 minus H1, right? Or H4, sorry. H4. No moving parts in evaporator. Work is 0. So Q dot is equal to M dot of H1 minus H4, which is equal to 7 kilograms per minute, times H4, which is going to be minus 99.56 kilojoules per kilogram, and H1 is going to be 244.09 kilojoules per kilogram. Solve that, I get 244.09 minus 99.56 times 7. I get Q dot in is equal to 1011.71 kilojoules per minute. So I know what my heat flowing into my system is, and I know what my heat leaving my cycle is. Alright, now let's find out what is the coefficient of performance if this system was a refrigerator. So, refrigerator, coefficient of performance. Well, how do I find that? If you recall, it's the amount of heat that you're removing from an environment versus divided by the work. So, if I'm removing heat from my environment, that heat has to go somewhere, and that's going into the cycle. Therefore, my coefficient of performance, it would be my Q in over my work. However, you might notice that this is in kilojoules per minute, and my work is in kilowatts, which is kilojoules per second. Well, my work of my compressor is 5.17 kilowatts, which converted is 310.2 kilojoules per minute. So my coefficient of performance is equal to 1011.71 kilojoules per minute divided by 310.2 kilojoules per minute, and my coefficient of performance is 3.26. This would be my coefficient of performance for a refrigerator. Well, let's do a heat pump. Well, remember, for a heat pump, I am pumping heat into my environment, which would be your room, for example. Well, to pump heat into something, you have to remove it from something else, and I'm going to be removing it from my refrigerant. Well, if you remove heat, you're condensing that fluid. So we would go up here to our condenser, and this is the amount of heat that is leaving our condenser. Therefore, that's the amount of heat that is flowing into your room. So, for coefficient of performance, we have Q out over work, which would equal to 1355.5 over 310, which is equal to 4.37. That is my coefficient of performance for this heat pump. Well, our next question is, if you recall up here, how can I make this a heat engine? Well, recall my last video, just flip the direction at which you're going. Now, what does that mean? Well, that means this. So here's my condenser. Here's my condenser. I'll mark it with a C. Going out here, I instead have a turbine instead of compressor. Going out, I have an evaporator. I'll mark with an E. Going up to a valve going back here. So this would be my state point 2, as you still recall. Oh no, I'm sorry. This is my evaporator. This is my compressor down here, or my condenser down here. So my fluid is going to flow through my turbine. I'm going to absorb in heat in my evaporator at my higher pressure of 9 bar. I'm going to get some work out of it, and I'm going to decrease my fluid to 2.4 bar. And then in my condenser, I'm going to reject heat into the environment, not Q in, Q out. This is how a heat cycle that I'm getting work out of it, would operate. My state points would be the exact same, only change is the direction that the fluid flows. So, and the Q dots. So, well, what's my efficiency now? Well, my efficiency would be the work I get out of it, which we're still going to say is 5.17 kilowatts, which is 310 kilojoules per minute. Well, what's my Q hot? How much heat did I start with? Well, if you notice, if I'm rejecting 13,000 heat to the environment and I want to flip it, I'm now going to absorb that heat back in, which would be 1,355.5. Have to use the higher heat. So Q hot would be 1355.5 kilojoules per minute. And my efficiency would be my work over my Q hot, which would equal to 310. Sorry. $310 divided by 1356. I'll just round up. And you get 0.229. So my efficiency is 22.9% efficient. That is how you would operate, how you solve this as a heat engine. Exact same steps though. I would know my state points here at point 2, up here. I know my state point values from what is given, and I write out my state points like I did here. I apply the first law of thermodynamics for control volumes for each individual part. Once I do that, I can then continue to solve my system, and I can find how much heat goes in, how much heat is rejected, and how much work leaves. Then I can find my efficiency, or I can find my coefficient performances depending on what I'm solving. So this is how you'd analyze a refrigeration heat pump or control volume heat engine type problem. If you have any questions, please leave a comment below, and more videos regarding this shall be uploaded, and there will be some fluid mechanics videos being uploaded shortly and a calculus series starting. From here on out, we will be covering control volumes on power plants, how those would operate. I'm going to show you how to do a Rankine cycle, Brayton cycle, a diesel cycle, and an Otto cycle. And those will all be coming shortly. Thank you very much. If you like what you see, please leave a like and subscribe for further videos. Thank you very much.